Hello, this is exercise 21A for predominantly students from Miss Stanley and my class as opposed to Miss Frovine's class, because you haven't done this one in lesson yet. But there might have been a few people who didn't do this from the other class because you was off. Abby springs to mind, for instance. So anyone who needs it, and there's obviously homeworks and stuff attached to this in due course. So let's get cracking. So this is all sort of set up regarding a famous mathematician. I'll just turn my pen on. So this is all a famous mathematician called Sir Isaac Newton, and the work that he did in what a branch of mathematics called kinematics. Kinematics is basically how things move. And Sir Isaac Newton, born a long time ago, 400 years ago now, but essentially the maths we still use loads and loads today, and lots of bridges, buildings stand up because of the calculations this man made. He basically realised at the heart of it that the force that you apply to something affects how quickly it will change its speed. So we call that change in speed acceleration. And so he essentially said big forces produce big accelerations, or force is proportional to acceleration, or put a different way, as we'll see in a bit, F equals ma. Now he did more than one law. The first law says that if you want to change the motion of a body, a particle, an object, whatever you want to call it, you need to apply force to it. Now that's not overly obvious, but it wasn't then, but now seems pretty obvious. You want to stop something, you have to push it, to stop it from moving. If you want to get something moving, you have to give it a push. That's really all it was. But the second law is much more impressive. As I say, it links the mass, the acceleration, and the force that gets from it. And F equals ma is the equation. F equals the force equals the mass times the acceleration, where the force is measured in newtons, obviously after Sir Isaac Newton himself. The kilogram is used for mass, and meters per second for the acceleration. Now, if we just go through a question or two on this, so you can see this in action. We've got a car of mass 600 kilograms. So we need to find the acceleration of the car and its velocity after 10 seconds. So very often these are questions which use that formula I just talked about, F equals ma, in conjunction with SUVAT, which you've already seen. And this certainly looks like one of those questions, so let's just go for it. I'm going to try to draw a picture. Yeah, I'll get this ready, working still. So it said we've got a car on a frozen lake. You have to forgive me for my dodgy drawing. Was it 600 kilograms, I said. So I often put the mass of the object inside it, so I can see it clearly. And it's subjected to a force of 420 newtons. So I'm just going to draw that. An arrow, 420 newtons. There we go. And the question says, what is its acceleration? So it's quite straightforward. We're going to use F equals ma. Force, of course, is 420. And that is equal to 600 times by the acceleration. So yeah, it's quite straightforward. If I take the 420, the 600 moves over, becomes a divide. 420 divided by 600 is the 0.7 meters per second squared that it says on the bottom. So that's worked out to right. What else is it after? Oh yes, that was right. Yeah, I wanted the velocity of this car after 10 seconds. And notice it does say there, assume there's no friction. So that's why we often get these questions on ice, because ice has very little friction. So if you want to simplify a question, that's one way of doing it. Anyway, so this is SUVAT I'm going to do. Get used to this. This happens quite a lot, that we do one thing and then we do the other thing. And what do we have? It says it's parked, so presumably its initial speed is 0. We know its acceleration is 0.7. I think it said 10 seconds. Yeah, find its velocity after 10 seconds. So I don't know the distance travelled, but I don't care either. So the equation we use is v equals u plus at. And that therefore means that u is 0 plus 0.7 times the 10, and obviously that is 7 meters per second. So we've got two answers there, both worked, so that's always a good sign. Let's move on. Similar question, this one actually, I remember this one. This says a car of mass 1200 kilograms is pushed with a force of 150 newtons. Calculate the acceleration. So almost identical to this. There's the answer again at the bottom, so we'll just make sure we can get that. So a car of mass 1200, there you go, is pushed. So I'm going to have the force coming into here, but other than where I've drawn the arrow, to be honest, it makes no difference at all. 150 Newton force. I think I just very quickly read it said you can ignore friction in this question. So F equals ma. Do it exactly the same way. The force is 150 equals the mass, which is 1200, times the acceleration. Therefore A is the 150 shared by 1200. And if you do that, you get, well, it's an 0.125, and if you do it on your calculator. There we go. What else did it say? It says if it starts from rest, how long will it take to reach a speed of 1.5 meters per second? So again, I'm not surprised by this at all. You get SUVAT in these questions, and F equals ma in these questions loads. And of course, the critical thing is you've got an A here and you've got an A over here, and that's why they like to join the two things together. So what did it say? It said it starts from rest, so U equals 0. How long will it take to reach a speed of 1.5? So that's 1.5. And of course, I already have calculated the A to be 0.125. And what's the thing? How long will it take? Yeah, sorry. So the T is what I'm after. So this is V equals U plus AT again. V equals U plus AT. The V this time I know. The 0 plus the A times the T. And obviously from here, if I just move it down here a bit, I get 0.125. T is equal to 1.5. And by division again, T equals 1.5 divided by 0.125. And again, on your calculator, you'll see that T equals 12 seconds. So, I mean, to be honest, those two questions are almost identical. So let's hope there's a little bit more variety in this question. A curling stone of mass 18, so we're given the mass, is launched across the ice. Again, ice, notice I talked about ice before as having very little friction. Launched across the ice with a speed of 2 and travels a distance of 30. Calculate the deceleration first. Now, I actually think this is the other way around, because they haven't told me any forces. They've told me a mass, but they haven't told me the force. So I can't yet find or use the F equals ma equation, but I can use SUVAT. So let's see if I can draw a picture here. So I'll draw there is my, I don't know why I've just coloured it in, but you get the idea. This is, I've now coloured it in, I've gone against what I've said. It's got a mass, it said, of 18 kilograms, but actually for this I don't need it yet, but I'll just write it underneath anyway. And as I said to you, I think this question is a SUVAT question. So we'll just see what we get told. Now it's launched across the ice with a speed of 2. Alright, so it said when it's let go, when they stop pushing it, it's got a speed of 2 and travels a distance of 30 meters before coming to rest. So all of this starts to make sense, and I presumably wants the acceleration. Calculate deceleration of the stone. Yes, of course I did. I remember now. So this time I haven't got the T, so a different equation. You should be learning these. V squared equals U squared plus 2AS. The V is 0 squared equals 2 squared plus 2 times the A times the 30. Okay then, so that effectively gives me 60S. And if I move that 4 from the 2 squared on the other side, And that should be minus 4. So S will equal minus 4 divided by 60. The distance travelled is minus a 15th. Yeah, that's what it says over there. I've written mine a bit better than this, but you get the same idea. Alright then, so now I've got the what was that? That wasn't I've written A, and that wasn't A. This was an acceleration, because it was from here. The S was the 30. But anyway, now I've got my acceleration. Always best to label it properly. What else does it say? Calculate the frictional force. That's right. So one thing I didn't show on this before was effectively it's trying to move this way. We've thrown it this way, so it's got motion this way. We know the speed, but a variety of times. But it is slowing down. If it's slowing down, the frictional force must be acting in that way. And I've written the frictional force as FR. Sometimes you call friction. Sometimes you write F just for friction, but I prefer just to sort of differentiate between friction and just the normal force letter used. So anyway, we've got friction F equals ma, and the only force acting this time is FR. The mass is 18. We now know the acceleration is minus a 15th. So the friction, if 18 times 1 divided by 15, is minus 1.2. Interesting, that's minus. The minus just represents the fact that it's a slowing down force. And it does say calculate the frictional force, the friction. So therefore, there's nothing wrong with then coming down here and saying actually the friction force is 1.2, because that's what it is, 1.2 newtons. The minus is fine if you've written it. So last question, I've got a couple of minutes to just do this quickly. F equals ma can also be a vector question. So let's see what this says. Yes, here we've got a force given to us as a vector, and we've got a mass 3.5. So it wants the acceleration. So if I just go over here, I'll write F equals ma. These are vectors now. Notice the mass isn't a vector, it's just 3.5. I've got 14 minus 21. 14 minus 21 equals the mass was 3.5 times by the acceleration. And obviously to get the acceleration I divide. So I do 14, I'll do the top divided by 3.5. I'll do the bottom divided by 3.5. And if I do 14 divided by 3.5, I get 4. I do 21 divided by 3.5, I get 6. So this is minus 6 meters per second squared. It doesn't matter, it's in two directions. The other thing I want is the magnitude of the acceleration. Now, you might remember from normal maths, not this mechanics maths, but normal pure maths, where you find the acceleration of a vector by doing the square root of, and you take the two numbers, and you go 4 squared plus 6 squared. Or have I done that wrong? No, I've done that right. I was worried about my signs then. Notice I don't care about it being minus 6, because I'm going to square it anyway. So 4 squared is 16, 6 squared is 36. And that gives me root 52, which is 7-ish. What's my answer say? 7.21. There you go. So 7.21 meters per second squared. Now, just bear in mind, you're going to need to do exercise 21A. The page number doesn't really matter, but there was something wrong. I can't remember what it was. I haven't got the questions in front of me. That there was something wrong with question 4. I don't want you to do that. Obviously, the easy questions, cherry pick them. Do perhaps just the first column, or if you feel you need more practice, do more than that. My email address, you probably have sussed by now, but just in case, colin.mccure at St Helens, all one word. Same, very similar to yours. I'm sure you can find it, but just in case, I'll write it there. On Moodle, you're going to have to get all your stuff on Moodle, but on Moodle you'll find these questions with the answers, and in due course there'll be a homework attached to them as well. So I want you to have a go at them and see what you can do, and email me if you get stuck. And there's 3 teachers willing and able to help you. So best of luck, and we'll call that quits.